Hey everybody, I want to go over a proof. Of course, it's not my own proof, but it's the proof of the well-known result, perhaps the most popular inequality or most used in physics, math, the Cauchy-Schwarz inequality. And I never knew the proof of it. I mean, I guess I remember it from linear algebra a little bit, but I never knew there was a proof that depended on the discriminant of the quadratic formula. So that's what I want to talk about. What we do is we actually start with an expression that kind of resembles the Cauchy-Schwarz. It's a squared expression, a squared binomial that's always going to be greater than or equal to 0. And then this is the algebra behind it. If you expand out this binomial, you get this expression, which is certainly quadratic. Now, if you sum up a bunch of things that are non-negative, you're going to get something that's non-negative, right? So we have this function c of x that's going to be non-negative. But what's interesting, I guess it's not that particularly that interesting. You can see right here that it's definitely in quadratic form. So I'm going to go ahead and use capital A just to avoid any ambiguity with the lowercase letters here. So this is in the form ax squared. And you see what's interesting here is your coefficient A is actually this entire summation right here. This entire summation behaves like your A, okay? Now right over here, this is in the form, we can write down plus bx, okay? Okay, and then plus, there's no dependency on x right here. So we can just call that our plus c, right? So you see, we have something that's actually in quadratic form right now. Okay, and we know that this thing is always greater than or equal to 0. And we're just going to focus, most of the work is on the case where it's always greater than 0. Equality is pretty easy to establish when that happens. But anyway, just to comment, how do we get away with bringing the x squared out? Well, the x has no dependency on this summation index, I. It has no dependency. So the x can come out as though it were a constant, right? But again, the A is equal to this summation. In this case, the B would be minus 2 times this summation, and C is just this summation. So you see, we know that this object right here would be your discriminant based on these summations. So we get right here, this is the same thing as B squared. I just thought it was neat. I had no idea it just pulled back to the quadratic formula. But so you have B squared minus 4AC is what needs to be recognized right here. All right. Now, how do we use it? Remember, there's 3 ways you can go with this. The discriminant can be positive, in which you have 2 distinct real solutions. It can be equal to 0, you have one real solution. It can be less than 0, where you have nothing but complex solutions. You see, notice I'm just going to focus on the case where this is greater than 0. We know it's always greater than or equal to 0. It's only equal to 0 when the BI's over the AI's is proportional, basically. So we're just going to focus primarily on when it's greater than 0. And being greater than 0, that means it has no real zeros, right? It has no real zeros. That means it never crosses, this function would never cross the x-axis, right? So it can only have complex zeros, which can only happen when this discriminant right here. And again, this is the discriminant. When this discriminant is less than 0, okay? Less than 0. Okay, now, so we're in good shape right here. We're forcing the discriminant to be less than 0 because we know there's only complex solutions. Now notice this is, I'm off the screen right here, but when you square this, you get 4. Now on the next screen, I'm just going to take this to the other side of the inequality, and we're going to have the Cauchy-Schwarz inequality. This will be 4, this will be 4 on the other side of the inequality. They will cancel, and you will have the Cauchy-Schwarz inequality. Let me clear out the drawings here, and let's move to the next screen. And again, y'all I wish I could stay on the same screen, but I can't. So what's going to happen, this will get squared, it'll become a 4. This entire summation will get squared. This object will get taken to the other side, and then the 4's will cancel. That's what you'll see on the next screen. Okay, and that's exactly what happened. I've just recopied that for you, and then we divide it by 4, and there you have it. This is basically the Cauchy-Schwarz for most of the cases we're interested in. And again, it would come together as less than or equal to if c of x was equal to 0 and we set the discriminant equal to 0. In this particular case, the BI's over the AI's would be proportional. When they were proportional, that is when the BI over AI, they're all equal. That would be the only case where equality actually held in the Cauchy-Schwarz. All right, hope you get